7.2 deals with integration by parts. So if you watch the video on it, then you'll know that if we have something in the format u times dv that we're integrating, then that integrates into u times v minus the integral of v du. And that comes from the product rule. If we add this to the other side, that's the integral of u dv plus the integral of v du equals u times v. And if we take the derivative of both sides, then essentially the derivative of u dot v is u dv plus v du. If we take the derivative of this side, the integrals cancel. Take the derivative of that side, that's what that means. So this integration by parts comes directly from the product rule. And it's just a rearrangement. So it becomes very useful when we have things that by themselves we're not able to integrate directly. So if we're looking at the integral of u dv, then we have to pick what part is u and what part is dv. Once we get u, then we're going to take the derivative of it to get du, and once we get dv, we're going to integrate it to get v. So the question is, what are we going to pick for which? Now on this one, we don't want to pick natural log to be part of dv. Why is that the case? Because we don't know how to integrate natural log. We know how to take the derivative, but if dv is natural log of t plus 3 dt, then to get v, we would be integrating that. That's not something we know how to do at this time. So that means u is going to be natural log, which means du is the derivative of that, which is t plus 3 on bottom, the derivative of that on top, dt. Which means dv is going to be whatever's left. So if this part is u, then t dt is dv. If we integrate that, then v is t squared over 2. So now we have du and v. So dv, the answer to that integral is u times v minus the integral of v times du. So if we've selected this part to be dv and that part to be u, then our answer is u times v minus the integral of v times du. Now, a couple things. There's still an integral in our problem, so we're still not done. Also, that 2 on bottom, it can come out front, and we can call this 1/2 times the integral of t squared over t plus 3 dt. Now, if you look at that integral, notice that is an improper fraction, so we have to divide that out. So let's go ahead and go to another page and say, how do we integrate t squared over t plus 3 dt? So we're going to divide t squared by t plus 3. So we have 1t squared, no t's, and no constant. And we're dividing that by t plus 3. So we put a -3 in the box. So bring down a 1, multiply times the box. Add that column, multiply times the box. So that's our remainder. T minus 3 is our quotient. So we just did synthetic division to be rewritten as t minus 3 plus 9 over t plus 3. dt. The quotient plus the remainder over the divisor. And then we can integrate this. T to the 1 bigger power over that power minus 3. We pick up our variable when we integrate a constant. And then integrate this. 9 is the coefficient. If that bottom part is u, then the derivative of the bottom part would be 1 on top. So that integrates into natural log absolute value of t plus 3. This is what we get when we integrate that. Back over here, then we have t squared over 2 times natural log of t plus 3 minus 1/2 times whatever we got for that answer. So the answer that we just got, copy it. Let's group that. Now let's copy it. So here, that integral is equal to this. So we have 1/2 times all of that. Squared over 2, natural log t plus 3. When we distribute, that makes that a minus t squared over 4 plus 3t over 2, or 3/2 t, minus 9/2 natural log absolute value of t plus 3. And then on the end, we have a plus c. So that was a little bit messy, but the key here was picking the correct u and the correct dv. So we want to pick something for u that we know how to take the derivative of, and we want to pick something for dv that we can integrate. Also, whatever we pick for u, we want it to be something that when we take the derivative, it becomes simpler. Some things become a lot more complicated when we take the derivative, so we have to be careful with our choices there. All right, so let's look at another example. Let's take a look at this one. So directly, we can't just make a substitution to integrate this. This is not just going to work as e to the u du, because if u is 4t, du would need to be just 4 dt. We could make that 4 dt, but that would be e to the u, that would be du, and we have this t that's extra out front. So we would have to ask ourselves, what would we do with that t? And we don't really have a good answer for that directly, because we can't just move a variable out in front of the integral. Constants, yes. Variables, no. So we're going to have to do this by parts. We're going to have to do this as the integral of u dv. So we need to see what is going to be u, what's going to be dv. So u, we want to get simpler when we take the derivative, and dv still has to be something we can integrate. So notice if we let u be t, what's the derivative of t? Well, that's just 1. So du would be 1 dt. So that means we can let the rest of it be dv. So to get v, we would integrate. If this, we could make this e to the u. If that's u, then du would be 4 dt, so we would need a 4 there and a 1/4 there. So that's just 1/4 the integral of e to the u du. So that's 1/4 e to the 4t. Remember, when we integrate e to the u du, we get e to the u. So 1/4 e to the u, where u for this integral is 4t. So that's our v. So as in the last problem, if we're integrating it by parts and we pick a u and a dv, then the answer to that is u times v minus v, or I'm sorry, minus the integral of v times du. Notice the good thing about u being t, du is just dt. So on the end out here, let's copy this. We have 1/4 t e to the 4t. We can bring this 1/4 out front, and then we're just left with an e to the 4t dt, which is something we can integrate. We don't have to do parts to integrate that. For this integral, if we let u be 4t, then as we said a moment ago, du would be 4 dt. So we would need a 4 there, and if we put a 4 here, we have to divide by 4 out front. We already have a 1/4. We're putting another 4 on bottom out front. So this is just e to the u du. So we have 1/4 t e to the 4t minus 1/16. And when we integrate e to the u du, that just makes e to the u plus c. So in this case, e to the 4t plus c. No integrals left to do, so we're finished with that one. If u would have been, let's say, t squared instead of t, then du would have still had a t in it. So when we put in v du, we would have still had a t here, and we would have had to go through this again. Sometimes we have to go through this more than one time in order to finish our process. What do I mean by that? Well, let's just look real quickly. If we had t squared e to the t dt, and we're doing it by parts, then we would pick t squared to be u, and we would pick e to the t dt to be dv. So du would be 2t dt. V would be the integral of this, which is just e to the t. So the answer would be v minus the integral of v times du. So we would have t squared e to the t. We could pull a 2 out front. And then to integrate this, we would have to do this integral by parts again. We don't directly have a formula to integrate that, so we would have to pick a u and pick a dv. So this time u would be t, dv again would be e to the t dt. Notice that takes care of this part and that part, so we've accounted for u and dv. So du would be the derivative of t times dt. V would be the integral of that, which again is e to the t. So we would bring this part down, minus 2 times the answer to this. Well, when we integrate that, that's u times v minus the integral of v du. We still have an integral, so we're not done yet. So let's distribute this -2. Now that integral is something that we can do without integration by parts. That integral is just e to the t plus c. Minus 2t e to the t plus 2 e to the t plus c. So if we get something that we have to integrate by parts, that gives us uv minus integral of v du. If we end up again with an integral that has to be done by parts, then we have to continue until we finally end up with an integral that doesn't require parts to do. Okay, if we take a look at this one, by substitution, we can't really integrate this directly. There might be some problems in homework that we could just make a substitution and integrate directly. And I say we couldn't. If we were clever, we might could make a substitution that we could use. But let's try to do it by parts, since that's what this section is about. So again, as we said, when we pick our u and our dv, we want it to get simpler when we take the derivative. If something becomes more complicated, then we want to maybe think again. And dv has to be something that we can integrate. So notice, if we take the derivative of that, it becomes a 1. So let's let the x be u, so that when we take du, we get 1 dx. That would leave the square root, or x minus 9 to the 1/2 dx, as our dv. So we need to integrate both sides. So v is the integral of that. Well, if this inside part, we normally use the letter u, we don't have to. If that's u, then the derivative of that is just 1 dx. So that would be du. So we just have the integral of u to the 1/2 du. And the integral of u to a power is u to the 1 greater power over that power, normally plus c, but we don't use the c until the very end here. So u is x minus 9 to the 3/2. So that is our v. Again, since this is the derivative of that, we essentially have u to a power, so u to the 1 bigger power over that power, so times 2/3, where u is x minus 9. So since that's the integral of u dv, that integrates in times v minus the integral of v times du. Now notice, since du, since the derivative of u was a constant, then that made that go away, so the only remaining variables in our integral are for that power. So we have 2/3 times x minus 9 to the 3/2, and we can bring that 2/3 out, and it's minus 2/3, the integral of x minus 9 to the 3/2 dx. So that's an integral we can do. If we let that be u, if that's u, then du would be just 1 dx. So that would be du. So that's just u to the 3/2 power. So we copy down. We have our 2/3 times the integral, and when we integrate that, that's u to the 1 greater power over that power, or times 2/5, and then plus c on the end. So finally, we have 2/3 times x minus 9 to the 3/2 minus 4/15 times x minus 9 to the 5/2 plus c. If we wanted to, we could factor out a common factor, which would be 2/3 x minus 9 to the 3/2. 2/3 goes into this and into that. Both of these have at least x minus 9 to the 3/2. We could pull that out front if we wanted to, but not completely necessary. So if we did, what would that look like? So if we pulled that out front in the first term, that would be gone, and we would be left with x. For this one, if we take a 2 out of the top, we're left with a 2. If we take a 3 out of the bottom, we're left with a 5. And then for our x minus 9 to the 5 halves, if we take an x minus 9 to the 3 halves out, then we're left with an x minus 9 to the 2 halves, or x minus 9. And then we have our constant. So either one of those would be sufficient. So let's take a look at this one. And let's pick out what's going to be u and what's going to be dv. So sometimes it's obvious. One choice for u, if we take the derivative of it, it gets simpler and simpler until eventually it goes away. And one choice for dv, when we integrate it, doesn't really get much more complicated. It just kind of stays the same, and we can integrate it. But here, notice if we pick u to be e to the x, well, du is the derivative of that, which is e to the x. If we let dv be e to the x, well, the dx, the integral of that, is e to the x. So regardless of which one we pick to be u or dv, whether we pick e to the x to be u or dv, it's neither getting simpler or more complicated. And the same thing is going to be true with a cosine. If we pick cosine to be u, du is negative sine. If we pick dv to be cosine, then the integral of cosine is sine. So not really getting any more complicated. In fact, both ways, we're pretty much getting the same thing. So we just have to pick one. Let's pick it this way. Let's pick u to be e to the x. So du would be e to the x dx. So dv would be that. So this is u, and that's dv. So v would be sine x. So when we integrate that, we would get minus the integral of v times du. Now look at that integral. That's still not something that we know how to do, and it's also the same type of situation. Regardless of what we pick to be u and what we pick to be dv, it's not really going to matter. They're both kind of going in circles. So let's pick u to be e to the x. So again, du will be e to the x dx. That means sine dx will be dv. So v will be the integral of sine, which is negative cosine. And the integral of that will be our new u times v minus the integral of v du. So if we distribute our negative, we have that the integral of e to the x cosine x dx, that's our original problem, equals e to the x sine x. If we distribute that minus a negative, we'll make that plus e to the x cosine x. Let's see, minus a negative, that makes a plus. When we distribute that, that'll make that a minus the integral, and if we rearrange that, that's e to the x cosine x dx. Wait a minute, that's exactly what we had to begin with. So we're going in circles. We started with this. We thought if we used parts, we'd eventually get to something that we could do. But after we did parts twice, we got back to the exact same integral we had at the beginning. So let's do this. Let's add this integral to both sides. Our goal is to solve. So if we add that to both sides and those cancel, we do the same thing twice on the left. So we have twice the integral of e to the x cosine x dx. And on the right, we have e times sine plus e times cosine. Well, if we want to solve and find out what that integral is equal to, we can just divide both sides by 2. So those cancel, so the integral of e to the x cosine x dx, we could write this several ways. We could factor an e to the x out on top and call that e to the x times sine plus cosine. All of that over 2, and then our arbitrary constant plus c. So that one was a little bit different than the other ones. It didn't have a definite point where either u or dv where they eventually went away. We just went in a circle, but nonetheless, we were still able to isolate what we were looking for and find out something that it was equivalent to.